This is the talk. Let me start my timer here. So this is going to be about what's new in pandas, mostly in version 15, but there's a couple of new features in 14 that I'll mention. So this entire talk, you can look at this GitHub that I put up. Both the notebooks are already rendered on there and the actual slides if you're interested. There's a few other notebooks on there, which I'll get to if I have time. If not, you can explore them there. Most of the data is actually there also, or links to the data. Just some interesting things. Okay. So I'm Jeff Reback. I'm a former quant, and I've been working on some projects at Continuum right now. I've been committing to pandas for the last few years. Since about mid last year, I've actually been effectively managing pandas, doing the releases and doing some of the features. So what's new in pandas? I'm going to talk about categorical data. This is actually a much bigger deal than I initially thought it was, and you'll soon see why. Timedelta's got a big revamp and became a first-class object in 15. MultiIndex Slicers. This is a new way of working with multi-index data frames. It was actually introduced in 14, but we'll explore it a little bit here. The DT accessor, and some grouping enhancements. Okay. So before we even start on these changes, I'm going to explain a little bit. I'm guessing a lot of you have actually used pandas, and some of you probably have committed to pandas. The internals can be a little bit intimidating, I suppose. But in reality, there were some big stumbling blocks that existed in the past to actually making any big changes. So two big things removed these stumbling blocks. Namely, there was a series refactor in 013 and an index refactor in 15. And basically, these just remove these from being subclasses of ND arrays. And anybody ever tried that? It's fun, but not fun for the people who are actually using them. So those were done. And there's this concept we have called internal blocking, which I'm going to go to a little notebook here. Let's see, where did I put it? Can everybody read this a little bit? So this is just a brief peek inside, explaining why we can support like a lot of different D types and a little bigger. Sure. Let's see. Okay. So this is just a brief introduction to show how we support different D types and how it's possible to support them at the same time. So I'm just going to I'm going to actually go into how these categoricals are constructed later. So we just have two different series right here. And I'm just going to show the floats for now. So if you look inside of this, these all have this underscore data attribute, and it just shows, in effect, this is just wrapping, the float series is just wrapping kind of an internal object called a block. So when we have a data frame of many different D types, and you can see here, a bunch of different D types, these have the same different internal attribute. And the interesting thing to note here is that, so the float blocks, if you see right here, were combined, this little 2 right here means they were combined into one block. So instead of keeping everything as sort of a columnar store, this is, it's columnar, but it's by D type. Except, you'll notice there's an exception here, the categorical blocks are actually kept separately currently. There's a technical reason for that. In theory, they could be combined, assuming they have the same categories, but that's a different issue. Okay, so going on. Okay. So, categorical data. What is it? So, everybody's familiar with categories. You have like gender, male and female, what meal I had, breakfast, lunch, or dinner. So, now why are these interesting? Well, there's basically 3 reasons to use categoricals. These are, just as by the way, these are basically like an R factor, but the pandas version. So, you can order by something that's non-lexical. In other words, you don't have to have ABC order. And this is always, like I want to order, 3, 2, 1 or something, and I just want to keep it like that and understand it like that and have my data know about that. So that's a very important feature. 2 is these tend to save actually quite a bit of memory, both in memory and on disk. And we'll show you some techniques in a little bit how to do that. Third, these can have meaning to users of pandas. A big example would be, for example, Patsy, which basically does expression parsing and feeds into stats models. This, it in fact interprets the pandas categorical type, which I'll explain that in a little bit. And so libraries can basically use the categorical data that exists in their own computations. Okay. So now, I'm sure everybody likes categorical data. Okay. Now, when I first started doing, did you get that? So when I first started thinking about adding categorical data, it was actually, I was going to add it to 14.1. So there's already a categorical type that existed actually way back through, I think, the .8 version. But it was not a, what we call a first-class type. It was, you could create it, you could manipulate it, but you couldn't put it in a data frame or a series. So that limited its utility. You probably didn't even know it existed. But it was there. So what we've done is we created a real first-class type out of this. And of course, this became a much bigger job than I ever thought it would be. So this is what happened. Okay. So now I'm going to show you some examples of categorical data. Okay, let's go up here. So I'll start real simple. So I've included at the top of the slides a link to the docs, appropriate docs. So basically, it's very easy to create a categorical series. You just pass it a list, give it a D type, and you get one out. And it looks like a series, except there's some different metadata at the bottom. Basically, this is an automatically ordered series. Okay, and I'll show you how to create a non-ordered one a little bit below. Okay, you can actually categorize anything. You can categorize ints if you really feel like it, or like daytimes, whatever you want. Generally, you do strings, just because that's what most people seem to be working with. So internally, these are kept. So this is an example of a series that is an int, and the values are actually an end array. But in this example I have up here, the values are actually the categorical variable itself. So this is basically the way they're implemented. So the interface looks the same, but the implementation is instead of being a numpy D type, it's actually a categorical D type. And this is just what it looks like. Okay, so what is a categorical? Basically, there's two parts to it. These are really pretty simple. There is a code. So think of this as like an enumerated type. There's a code which basically maps your categories to an integer. And then they're the actual categories. You may note that I'm using this little thing called s.cat. So this is also something that was introduced. We'll show you later the .dt accessor. This is the cat accessor. So it allows you to do operations on a series. So you're probably familiar with the .str accessor. So you can treat a specifically D-typed series and do special operations. So for strings, you could do things like extract or match or whatever you want to do. So here, if you have a categorical, you can say, oh, give me your codes or give me your categories. You can actually do mutating operations also, you can look in the docs how to do that. So this is an ordered categorical. And the way these are constructed, so you basically factorize. Again, it's just, you just assign integers more or less to the different types, the different unique types that you see. So this is how to example to construct a non-ordered categorical. And notice it looks almost exactly the same, except instead of having the little less than signs, these are just little commas there. Okay. You can do operations on these. You can do like min and max, and get logical orderings rather than lexical orderings. These actually happen to be the same, but that's what they do. Notice if you have a non-ordered categorical, then certain operations are prohibited. Okay. And, oops, I don't know why this is not on here. So you can treat a categorical just like any other, or a series that happens to have categorical D type, just like any other series. You can do operations on it, and it returns the same like D type. And okay, so here's a little bit more, little bit bigger example. So this, we're constructing a frame that has two columns. One is just a random integer, and one is so I'm using this function called pd.cut. Again, this existed previously in pandas, but in some sense it was not useful because it returned something which didn't fit into the rest of the pandas ecosystem. It now does. It now generates a categorical variable. So you can, what this little statement is doing is it's saying, hey, take these integers and put them in the bins. And I'm labeling the bins. These actually happen to be strings. Okay, so you'll see here the D types of that. And if we select the series again, we get back a categorical variable. These happen to be, this is the ordering for them. Okay. So getting to the first use case that I mentioned before, you can sort. And I'm reverse sorting here just because it's interesting. And you can group with another non-categorical variable, just so you can treat these just like any other variable. You can group by. This actually worked before in prior versions of pandas, but again, you generally didn't have categoricals laying around, so it was hard to do. Now, the interesting point to note about this is that it's preserving all of your categories in the return here. Normally, group by doesn't do this, and this is actually a point of debate whether it should do this. And I actually think it should, because you're working with a limited set, and you pretty much always want to see that set, and by default. And you can always drop them, of course, but it just sort of makes it's natural to me to do that. But, further indexing operations. Sure.
Where did you set the order of these?
The order. Yeah, back up here. I didn't actually set the order. What I did is I ordered them. These were created by, okay, so there's a default that creates your order. They will be treated as ordered unless you tell them not to be ordered. This apparently is some kind of our default, so somebody suggested that was a good idea. If you don't think it is, then let me know.
That's just for ranges. Like if you have some.
You could order arbitrarily.
Then you'd have to supply what is the.
The way you do that is you, let me go up here. So you can look at the categorical constructor, but there's actually a way to, so it will automatically factorize it, but you could also supply the categories. You could even supply, I had this example, but I took it off. You could supply effectively your own, bless you, your own factorization if you want. So there's various ways to set this order. You can reorder them afterwards. There's a lot of operations I could actually do. Okay, just going on here. Okay, so something that's useful for, let's say, other libraries, there's this thing called get dummies. And essentially, this transforms a 1D variable into a 2D of indicator variables. And I think this is called, the sklearn guys call this one-hot encoding, something like that. So that's a pretty useful thing to do. Something that's also interesting is invert dummies, basically reverse that process. Okay, that'll become a real function at some point. So here's another big aspect of why they're useful. So right here, I'm going to construct two frames, one an object and one a categorical. Okay, basically I'm just taking. I'm going to show you. Actually, do it here. So I'm doing it with a float also, just because it seems interesting. Do this here. So this is something that I discovered sort of recently. We also added when this comes up here. So this is 500,000 objects. I don't know why it takes so long, but it does. And it's, okay, so just regular old frame here. So in 15, we add this little thing called memory usage, and this is on by default. And in 15.1, we added this little plus sign there because it turns out, so this is something I just never knew. So when you actually have a string in a NumPy array, well, what do you do with it? How do you represent it in memory? The answer is it's an object pointer. So the memory that's shown here is only an int 8, int 64, 8, in other words, 8 bytes per object. That's it. And you'd be like, well, that's wrong. And the answer is it is wrong, because that's why the plus is there. So, but however, now I'll show you how there's 3 different ways to figure this out, and there's some issues, and I'll go through them in a second. So this is what I believe Python actually does. And so what it does, so you can see this system get size of, and iterate over each object. And in Python 2.7, I believe this is actually pretty correct. Okay? So that's the additional memory taken up solely by the objects that exist in memory. It has no concept of duplicates in memory at all. I've been informed that Python 3, in theory, will what's called intern strings, essentially construct the categorical, but only for like 1 and 2 length strings or something like that. Could be wrong, but that's what I've been informed. So now, what if you actually do this? So the reason this number is much bigger than this number, which I'll show you. So this number is effectively the number of more or less bytes that are represented here. Okay, this number apparently Python does something like 37 bytes per string that you have for, and it's called garbage collection overhead. Never knew this. This is why strings take up a gigantic amount of memory. Well, that's why. It's crazy, but that's what they do. Okay, now there's another way to represent things in memory, and that is as a fixed length blocks. Okay, so basically you construct a block which is the maximum length of all your strings, and that's your memory block. Okay, so we could do that too. So this will convert it to an S20. That was the longest string I had. And here's the approximate memory of doing that. And this is marginal to my diagram up here. That's why I have this little subtraction doohickey here, which subtracts out the original int8 pointers, or int64 pointers. So in theory, you could say, hey, this takes up about 17 megabytes of memory, this structure here. Okay, so now let's look at the categorical version of that. Right out of the box, it takes up a lot less. Okay? Why? Very simple. These categoricals are represented by int8s. So you have, and that's it. So it becomes very simple. I'll show you that in a little bit, in a couple of seconds. So recently, this is actually in master, and it will be released in 15.2. So I enabled storage using HDF5, and actually another fellow enabled storage using Stata to basically save. Stata could already actually read categoricals. Now it can actually save them also. So you can see this is just saving as object and then saving versus categoricals. And again, it's a fairly big differential here. Again, this is solely because HDF5, the current implementation is a fixed length block. Okay? Just for your edification, this is how they're actually stored. They're stored as a table and then another table of the categories, basically. So you can, this makes it, notice this has length 5. So that's the actual categories. Okay, and just to finish up in categoricals. So this is how they're actually stored in memory as int8s, whereas a normal object array is stored as objects. Okay, so that's categoricals. Okay, that's my little can of worms. Okay, next feature. So in 15, we added, I'll say, first-class support for time deltas. Now, time deltas actually existed beforehand, and they existed in series beforehand also. But the underlying object backing the time deltas was, and it actually still is an MP time delta 64. And you'll say, okay, well, great. Did you change anything? And the answer is, what happens is, if you use date times at all, you get back, when you try to get a, when you look at the underlying data, you get back a timestamp with a capital T. And so it's a subclass of a datetime.datetime. So what we created was literally a time delta with a capital T, which is a subclass of datetime.timedelta. And this is all done in Python, so it's very fast. So it looks almost exactly like the Timedelta Scalar type that exists in Python, and it's extremely interoperable with it, with a lot of additional features on top. And we'll show that in a second. So here's my pictures of time deltas in case. So this is okay. So what is a time delta? Time delta is basically a zero-based index. And they're used a lot in, say, like my friend Phil, he uses them in, like, when you're a neuroscientist, you want to keep track of things from 0. You don't care about the date times, you care about 0 to 1 minute to 2 minutes to 3 minutes, whatever. And apparently people used to use floats for this. Fine, great. But this is a more logical unit to use. And you can use floats too if you like. Here's my next little graph. And the last, so I had to have some pictures. So this is the time is passing. Okay. So here are time deltas. Okay. Brief introduction. Hopefully your time is not screwed up. Okay, so time deltas work, again, there's a link over here. They work like, you can construct them from string likes. Interestingly enough, when you construct with a negative time delta, you actually get what's called a reduced form. This is actually the same exact thing that Python does. Just how it is. These represent exactly the same moments in time. It's just how it shows it. So you can construct using arguments. You can construct using logical units. These are the same as the NumPy units, actually. So like H is hours. You can construct ranges using 2_time delta. This actually has existed also since 14, but it's enhanced now so that you will get back a TimedeltaIndex object rather than, you used to get back a series actually. So you can construct multiples. And there's a new function, time delta range. This is very much like datetime range. it gives you back a range. The interesting thing is you can give it a frequency. So you now have a regular index here. So you can also create these in other ways. You can create, start with a date range, and then you can subtract off something. So these are just two displays of the same thing. I'm displaying the actual underlying objects here. So this is well, it's a regular increasing series. So it doesn't actually have a frequency because it's increasing. You can perform operations like you can add things, you can add a day. You can do, there are some operations that will raise, like you can't add two dates, for example, logically. But you can certainly subtract two dates to get a time delta. Time deltas ops look very much like other operators. So you put them in a series, you have time delta 64. Again, just like we stored date ranges, these are stored as an underlying, they're stored in nanoseconds underlying and displayed with a nice output format. You can do reduction type operations. So you can take your data and you can count it, mean it, max it, whatever you want to do. So there's a couple of special operations that exist in time deltas. The first one are called frequency conversion. So this is taking something, say like, and converting to seconds. In other words, you're converting it to some float data. So you're saying, how many seconds does this represent? Or minutes or hours or whatever you want to do. And you can also accomplish this by dividing. This is like a true division. And I'll show you why this matters in a second. So you say, oh, you have two different ways of doing this. Well, the answer is yes. Because the first one is floor division and the second one is true division. I don't know if it's the best idea, but that's how it is. And this shows up here. So, for example, this is a floor division and this is an actual true division. So you're representing like a fraction of a day here. Okay? So the next thing I call is place value. This is a little bit different than other, we'll say, units, where place value is sort of implicit. Here it's explicit. So I want to say how, and I'm using the date time accessor here, and I'll get to that in a few minutes. But okay, if you look up here, and I read this, this says, 1 minute, 20 seconds. Well, that's what I mean by place value. So I want to say, well, 1 minute and 20 seconds. So those are the place values. I don't know if it's exactly the right term, but it seemed interesting. So one thing you can do is say, okay, give me the components. Give me all of the place values. And now you could do this with regular time deltas too, but I just find this a little bit less intuitive. So this is just a pure time delta, 1 second. So that's 1 second there. And total seconds. That's our notion of frequency conversion. Okay. So one of the points of this was to construct the time delta index. So that's what we're going to do here. We're going to construct a frame with one column as just a column of numbers and then a time delta range. And then we're going to set the index at the very end. So now we have a frame with a time delta index that happens to be regular. Okay, 20 rows. So you can do operations just naturally like you think they were. Show me the, everything that's essentially 4 days that's inclusive in this range. This is a special, I'll say, feature of pandas which does this type of slicing. So if you have a datetime index or a time delta index, you can actually use what's normally, this is normally a column accessor. This I always found confusing in pandas, and I'm sure everybody else does too. But you can, an operation when you use a string gives you a slice. So if you do a slice on the primary accessor, you actually you slice the rows. A little bit, it's natural in code, but it's a little bit counterintuitive. But it has always existed, so therefore it's backward compatible. So one natural thing to do, of course, is resample. And works just like other datetime index resampling. Okay. You can do other kinds of interesting index ops, and you can get back special indices doing that. It'll just interpret what you're sending back. So this is, I guess, interesting. I don't know. Here's an example. I'm just going to show you. So this is a group. Actually, it's a group by example with time delta. So I just pulled this off of Stack Overflow at some point in time. So constructing, so you have a data frame, and we construct the diffs. So we construct the time deltas directly. And this is something I suspect is actually a fairly common operation, which people do is, okay, so I want to then group by something that's, show me the 30-minute grouped intervals here. Okay, so easiest to construct a Boolean array. And here's the magic operation I call. So if you do this, if you cum sum them, a Boolean array, you then get, in effect, a grouper. Okay? Here's another example of doing almost the same thing. This is a little bit more complicated example. So this is another example. So someone said, I want to track when this number changes. See this value? It changes here and here. This is like breakpointing. So it says, okay, so you diff the series and you get where, see where the minus ones are? Well, you can either do it with the ones or the minus ones. We're going to do it with the ones, actually. So this is what I call sectioner. So I'm saying, give me a grouper and say, show me where the values change. This is a little, it looks like magic, and I guess it is. You have to stare at it for a little while, and then you're like, oh, this gives me a grouper. Okay? Same one as above, but it's a little bit constructed a little differently. And then, of course, you can simply group by it. And then you could do a lot of type of calculations. Hold on, get through here. So we're going to group by this and say, give me the last value minus the first value. I mean, you can construct an infinite number of operations here, but this was just the example from the question. I think I have this somewhere. If you don't want, here's a similar type of way, but I say, okay, instead of reducing in the group by space, I simply want to, for every value, transform it. This is another way of doing it. Okay. Getting even more complicated. You'll notice that these indices that are returned are actually, they're basically in group by space, so they return the group number in effect. Okay, so this is a transformation operation to return my original indices. This is a little bit non-intuitive, and so this is something I think we're going to work on in the next version to make this a little bit more natural. Okay, that's it for that. Okay, next topic. Oops. Okay, so now I'm going to talk about multi-index slicers. So everybody, or at least hopefully everybody, uses multi-index slicing. So multi-index slicers were introduced in 14 to make slicing a little bit more intuitive, make the syntax a little bit easier to use. Technically, they replaced the need for using .xs, which is the cross-sectional operator, and allow you to slice multi-dimensions somewhat easier. And the biggest thing is they allow you to set, which is interesting. Okay, here's my picture for this. The answer is multi-index slicers. Okay. Okay. So this is a brief introduction here. Hopefully we have time for this. Let's see. So there's a little bit of boilerplate in actually constructing a multi-index data frame that, for my purposes here. This is another actually thing introduced in 14, this multi-index from product. This actually is a pretty cool thing. It allows you to construct multiple levels from a list-like, and it'll give you essentially a Cartesian product of all of them. So you could say instantly I have 4 times 2 times 4 times 2, which is 64, and this is going to be my index. And then here's my columns, and this is what it looks like. Okay, nice little frame there, 64 columns, and we have both a column multi-index and a row multi-index. Okay, so something to note up here is I'm sorting. You always should sort your multi-index frames. This will be clear later. Any type of indexing operations pretty much require this. Now, however, if you don't want to sort them and you don't have need for direct indexing, that's fine. Because it may be an expensive operation. That's why we're sort of forcing the user to do it. Potentially could be expensive, so you don't necessarily want to do it. So this one happens to be sorted because I forced it to sort. And here's an example of, okay, I want to sort by my third level. So instead of having like C0, C1, C2, C3 repeated, so now we have, C0, C0, we're sorted by that column, okay? That's what sort level basically does. And now the sort level has been in effect invalidated. Okay, it's not sorted at all anymore. So in prior versions, you could still do this, but this is how you would access, say, the third level. Okay, so give me the third level that is equal to C1. There's a couple other ways to do this, but this is the way that is sort of advertised, or at least was advertised. Okay, forget this drop level for a second. So I get a frame that's 16 rows. So I selected all the C1s. Okay, great. Using multi-index slicers, I can do it like this. Okay, so I'm providing a tuple to lock, and I'm saying, okay, don't slice anything on the first level, don't slice anything on the second level, slice me C1 on the third level. Very important to note that I'm also slicing the other axis, or at least I'm putting this colon here. This is actually, it's technically not required in certain circumstances, but I would say like always do it, because otherwise this could be interpreted in a slightly different way sometimes, depending on your axis. It's just safer always to just do it. It's just easier. However, that syntax is a slight improvement. We can make it much better, actually. So we introduce these things. I'm not even sure what to call them. It's technically a class. I'll call it a helper class. So this thing called pd.index slice, it's just a class variable is all it really is. But what it allows is to do a nested get item. So it improves the syntax, at least in my opinion, a fair amount. And so now it becomes clearly, okay, I'm putting an empty, I'm slicing empty on that, or not say empty, I'm slicing, give me everything from that index, from that level. So everything, give me C1, everything here. So that's a reasonable improvement, I suppose. And it's the same frame. Okay. You can, of course, slice, oops, you can give it a list. And of course, you can slice on multi-levels. And this is something that was really simply not possible in prior versions. Now, you could certainly do this by, say, resetting the index and then using a Boolean selection. This is actually much faster, actually. So this is why this is sort of useful. Because this is computing, like the implementation of this is actually, it's computing into the, we'll say the compressed space here that's represented. So now, of course, you can also select on multi-axes here. So now we're slicing simultaneously the index and the columns. So hence you can basically go crazy if you feel like it. And of course, you can use this helper function on both axes to make it even more clear what you're doing. Now, here's the big win, I feel, is you can then perform operations which only affect that subset. You can actually, even on the right side, put another frame, which will be aligned automatically. I didn't in this example because I didn't. Okay? There's another thing you can do. You can add in a Boolean selection on this also. Now, this is a little bit, we'll say, trickier. And the syntax that I think works the best is actually, and I normally never recommend anybody to do chained indexing, but you can do chained indexing here. So the reason for this is it's just a little bit like, look at this statement down here. You can actually put the Boolean selection in the main indexing block, but I don't find this as intuitive. So this is like a work in progress here. Maybe there's a better way to do this. Got to think about it. Now there's another way to do this. This was, and I'm going to switch my example here a little bit, just to make it a little more clear, just to give it a smaller result frame. So here we're selecting A1 and A2 on the first level and C1 on the third level. This is a feature actually Phil wrote for the, and it actually exists in 14. You can do, in effect, a query language almost. So this is df.query, and it allows you to actually work with your indices in a fairly natural way, actually. So in this particular case, this looks like the best way to do it. This is actually a slightly modified version of Python syntax. It's processed as a string. This is as opposed to, say, how Blaze does it, which actually evaluates the Python. This evaluates the AST, actually, and it's slightly modified from regular Python syntax. So the one feature we'll probably add at some point is the ability to do, in effect, using a dictionary as instead of a tuple. Say you have a really many levels, like 30 levels or something. Well, you don't want to write out each indexer. That's kind of error prone. So if we provide like a dictionary interface or something like that, might make sense. Okay, so that's multi-index slicers. Okay. Next. So .dt accessors. So just as there's the .str accessor and the .cat accessor, there's a .dt accessor now. So the whole point of this is to say, hey, I have a particular D-type series and I want to get like the hours of it. I say, well, that's a normal thing to do. If your values are a date time, it makes perfect sense. If they're not, it'll actually raise an error because it doesn't make sense on, say, an integer series. It just doesn't make sense. So, in fact, the utility of this, I'll show you in a second, it allows you just to tab complete on the D type of the series itself. And here's another reason this is done in this particular way. Say you have a series like this. You notice the only difference is this is, the index is, I think I offset it like 12 hours or something like that. Or I did something here, yeah. I offset it 1 day. So the problem is if I say, give me the hours of this, well, it's not entirely clear what you're asking for. Are you asking for the index or are you asking for the values? So this is why it's now explicit that you could certainly do it on the index, but it'll explicitly do the values, which is in line with how the other pandas operations work. So here, so we have, so this is our little example here, and this is how you used to do it. You would actually have to wrap an index around it. So that works cool. So this is how you do it now. Yeah, and so the advantage of this is then you can do stuff like this. So you get tab completed with the accessors that work for that D type. Makes it natural, or at least in my opinion, it makes it natural. Okay, now, so why would you want to do this? Well, you want to do some selections and you want to make them as natural looking as possible, and there you can. Okay. Now, of course, this works for other D types. It works namely for, of course, date times, and it works for time deltas, and it works for period index types as well. So here, and you can, we looked at this before in the time delta section, but I'm just sort of repeating a little bit here. Okay. Now, it actually is even more interesting. You can chain these ops. So a very common thing I see is people saying, oh, I want to convert to time zones. Okay, great. You can do that. And now you can take that time zone and convert it to a different one. And it's returning a series that's indexed by like the original series. This does not have to be numbers. It just happens to be in this case. It could be whatever, and it'll just keep returning it. And there's even some operations that return a scalar in this case. So tell me the time zone of that resultant series. So that seems reasonably useful. All right. Okay. Okay. So now I'm going to show you a couple of examples. These are somewhat more advanced group by examples, and I'll show you, you'll see why I'm doing this in a second. Okay. So we basically introduced, just like we have a helper function to do index slicing, we have a helper function to do group by now. And it's purely to specify how you want to do a group by, because it was a little bit awkward in some cases. So going up here. I'll show you what that means. So this is an example, random data frame here, where you have a couple of columns and a date column and quantity. So, pretty straightforward here to do this. I'm going to group by buyer and select my quantity and then count it. Okay, it's very straightforward. Now, in order to resample it, though, I have to then set the index on the to the date column, and then take the quantity and then resample it. So it's sort of like all over the place here of what am I doing. Okay, it works. It's just a little bit syntactically challenging, if that's a word. So, okay, and then here's a further example of doing a chained group by, and I'll get to why the syntax should change, or it has changed. You can still do this. So here I say, okay, what I want to do, I want to first group by my buyer, and then I want to select the quantity, and then I want to resample that thing. Okay, so I'm doing a chained or multi-group by. But the way I'm laying it out is not the way it comes out, because the groupers are in this order: the first buyer, then resample. Okay, fine. Here's the new way to do it. So you use this little helper function, group by, and then you keep each group by operand, I'll call them, where it should go. So you have buyer. This is in effect, it's just a shortcut, syntactic sugar for using a PD grouper actually, but you can still use buyer. And then I'm saying, okay, this operand right here, I want to do in effect a resample operation. Okay. So I'm going to say, I want to take this column, date, and I want to resample it at 1 day intervals. And then I want to take the quantity and I want to count it. Okay? And I get the same result. Now, the reason this is useful is because then flipping it around is very trivial. Just flip the order of the operands. It makes you operate in the order that you would naturally use it. It's a little bit more boilerplate, but potentially could be more interesting. Now, it also allows you to chain multiple group bys now. So you can add a third thing on there pretty easily. And remember that we're returning here a multi-index based upon your index, the number of levels of the number of operands. Okay? So this is a feature actually is currently a bug. You'd want to be able to actually say, okay, I want to say group by this thing, because I'm doing a result here, on the level of buyer. Okay? So this is, it's not hard to fix, it's currently a bug. You can actually, oops. So this is the result, which is going to be, of course. Not that interesting, but it's there. Okay. All right. Let's see. Okay, I'm going to talk about a couple of things where we're going to go, and then we'll see if I have time to. What time do I have till? Oh, I got 8 more minutes. Okay. Actually, before we do that, I'll show you just a couple of brief examples. So I'll give you another example of why I'm jumping back to categoricals for a second. So this is a standard. I don't know about standard. This is a data set which is based upon some Fannie Freddie data from I think 2013 or whatever. I have the link up here, and so I basically took. I think there's 2 files here, and this is just showing you how to read it in, and I wrote out the HDF5 just because it was faster to do it. This is all as object data. Okay, so I read it in and I said, okay, here's what I got. This is starting data, 600 megabytes. Great. Well, then, and this is what it looks like. It's all these great numbers here. That's really intuitive to me. So what I'm going to do, I'm going to spend a little time and assign some meaningful values, and I'm going to assign them actually. Not only am I going to assign values, certain ones I'm going to actually order, and certain ones I'm not going to order. So here's an example like vendor. Well, I'm going to make them. They're either and I looked up in the index of what these values mean, and that's how I figured this out. So they're Fannie Freddie. That's not it's just a collection. It's not an ordered. Whereas things like income ratio or something is actually an ordering. Now it doesn't have to be. I just made it one, and it seems reasonable that it is. Okay. So I did this for this data set. Well, fortunately or unfortunately, is just composed entirely of object type data. So normally you sort of want some other type of data to interact with it, and we'll make that up a little bit lower on this. So I basically converted pretty much every column, I think, to categoricals. The other thing, just to note, that so up here, notice everything is not null. Why? Because you can't really see in this little example I'm doing here, but there are values which effectively represent nulls, but they're just a number. It's like number 9 or something represents nulls. So what I did over here is basically putting a nan in the category assignment basically treats them as missing. So sometimes you want to know things are missing. So we initially had like 600 megabytes of data, and now we're down to half, actually. And we also have all the null assignments. So this seems like fairly useful. Okay. And you could do interesting things. You could say, oh, describe. This is actually another new feature that we added. So you can, on certain type of operations, you can have include and exclude for certain D types. So if we had also numbers like a float column or something in here, you could say, oh, just give me the category data. Because sometimes describe in particular has a slightly different output format for categorical or object data and float data. It's natural, right? You don't care about the standard deviation of your objects, but you do for floats, say. So, and then you could do things like you can actually create a multi-index from this. And in fact, this is what people usually do. It says, okay, let's organize it. So I'm going to use some of the features that we showed before. We're going to actually, so I set the index to vendor, MSA, and purpose, and then it said, okay, show me, where percentage minority is this one, and then it's a purchase. And I did that on the different levels. So just showing an example of how to slice this. I'll just go through this briefly, but you can use all kinds of cool pandas operations to do this. And this is actually a fairly big data set. This is 5 million rows here. This is all in memory. If it's bigger than that, then you need Blaze. Here I'm actually creating a numerical column. Why did I do that? Just to get some numerical data in there because it didn't have any. So I said, okay, I'll create one. A common thing to do with categoricals is actually to do a value count on this. And this is, I'll show you like one new feature. We need a categorical index. Why? Because once you value count a column, you almost always want to index it like that. I'll show you that a little bit later. What did I do here? You could look through this data set. I'll just show you one more example here. This is just another, this is not interesting. Hold on. Let me show you one more thing. I have one more example and then I'll just finish up. So in this time deltas 2 category here. So I downloaded from this site here, I think I downloaded, so I downloaded daily data for IBM. It was actually, I think it's a Norwegian site, something like that. So I'll show you this, I had to convert the dates. So that was sort of slightly interesting. Let's see, what did I do? Oh, so, yeah. So I created here a time delta column, okay? And so I said, okay, I'll look at some of it. And then here was the interesting thing. So I said, okay, I'll value counts on the differences in time. I said, okay. And then you can find interesting things about it. And then I found this one, like, oh, didn't trade for 6 days. That was that date. Everybody knows that date, right? And, well, you could do interesting things. So now, you can look at the rest of the example on your own. Let me just finish up the, okay. So what's in the future for pandas? So we have a couple of the, I have one more notebook actually. So one thing that's, one more. One thing is is being added, actually will probably be in the next version, is the interval index. And I'll just show you the motivation for this. There's this fellow actually working on this. So index is now pretty easy to subclass. So give an example here of, this is created, so we're creating a categorical variable, you see right here, called range. Now, if you group by this, group by the categorical itself, look what you get back, okay? You get back a multi-level index where the first one is actually, it's not a categorical anymore. Well, it is, but they're strings, okay? So this is the motivation for, it's a special type. This is actually an interval index. It's obviously just strings right here. But hopefully the next version we'll be able to actually convert this to a type of index like that. Okay. The other things that we're looking at adding are a categorical index. And then this thing I've been floating called pd.string, which is in effect just a categorical, but it has one additional property. So the idea is I would like to see just automatic conversion of all object types to string. Okay? You can't do this with categoricals actually because there's a specific restriction right now where you can't, if you concatenate 2 categoricals, they must have the same categories, okay? And it's just an enforced restriction to avoid basically doing things which you might not, it needs to be a user-initiated operation. So, however, when you have strings, you don't care about that. You just simply want to shove them together and call it a string. So that's why we actually need a slightly different type for this. But it is really underlying it is a categorical. Another thing I think we're going to add are time zone aware datetime blocks. In other words, right now if you notice they're represented as object D type. So this is slightly inefficient. So we can easily add things like that. So, and then sort of 2 other things that we're looking at. One is incorporating a library called Dyn, which is actually, these are Python bindings around we'll call it a NumPy replacement, okay? And one of the big things that we're going to, I think, try to add is this will enable integer NA support, okay? And this is going to be basically as an optional library to pandas for some time. Maybe eventually we'll add it as full time because this has other features that we'd like to incorporate, namely things like variable length string support. Some interesting things that are implemented in a C++ library that we can easily add to pandas. And the last thing was just thinking about, instead of backing the actual data in pandas data frames via NumPy arrays, you could actually back them using a library called bcalls, which is basically provides chunk compressed on disk arrays. So you could have in effect a virtualized data frame. We'll see how complicated that is. So please contribute. We actually have lots of contributors, but there could always be more. So touch us up. Any questions? Shoot, stop. Okay. Yes.
For the categorical variables, is there a trade-off for if you have like 30,000 categories, does that become prohibitively large compared to strings, or are categories one to another?
So the question was, is there a trade-off between categorical and object type? The answer is yes. So the assumption is that k, your number of categories, is a smaller fraction of n, your total length of your series, okay? So if you are talking, however, even with 30,000 categories, even if you had 50,000 length, it's probably worth it. So yeah, if you have 31,000, okay, I'd say, okay, just use strings. So it's up to the user to make that trade-off, but you're going to save a ton of memory doing that, and everything will be faster. Okay. Any more questions? Sure.
Okay, so when you're working with, when you're turning a kind of category into a dummy variable thing, right? So traditional like econometric or statistical practice forces you to take out one, because or else you have to take out one of these categories in order to refresh them. Right?
Okay.
I know like certain software like Stata have stuff like that to do that pretty easily. Do you guys have anything like in terms like to kind of go between the two so that you can kind of figure out which one you're not using or something like that?
So you're talking about basically doing a stepwise type regression, right?
Not only a stepwise regression, I mean like you're doing like you're turning these into dummy, you're turning dummy variables. You need to, if you're doing dummy variables, you have to take one out.
Patsy does exactly this. It will provide a, what is it called, an n cross n thing to do that, I believe. Any more?
Is the category in the underlying NumPy array, is it light or what is it?
They don't actually exist in the underlying NumPy arrays. So this is a pandas D type in effect. So what happens is the number, the way the D type of the category, the codes are determined, it's really as a function of the length of your categories. So for all intents and purposes, usually it's an int 8, unless you have more than I think it's like 2 to the 7th or something, and then it'll just expand to an int 16. Okay, so it's a function of that basically. Anymore? We're out of time. Okay, so that's it. Thank you.